Yeah, that's too fast. Hello Internet, my name is Quinn and this is Blondihacks. I'm starting on a new tool building project today. I'm going to build the ML18 die filer. This is a kit made by a fellow named Andy Lofquist out of the States, and this kit was sent to me by a friend of the show Nick as kind of a shop warming gift. It's been in my build queue for quite a while, but it's time to build it. This is a very interesting kit with a lot of big, complicated castings. If you liked my steam engine build, the big steam engine build that had a lot of sketchy things done on small machine tools, this is going to be another one of those. So let's go. Here is the ML18 die filer kit, and there are some very impressive castings in this. You see the table there that I just set down, and here's the star of the show, the base casting. This is really a very impressive piece of cast iron. You can see there's quite an elaborate core that's been done in the center of it there, and it's a very complex and intricate piece. Here are the drawings. They're all hand done in a traditional drafting style, so they're quite charming, and they seem to be very complete, so no issues here so far. A very reasonable question to ask is, what the heck is a die filer? Now I know what you're thinking. No, die filer is not a way to threaten the apprentice. In short, it's an automated filing machine. It's kind of the machinist equivalent of an oscillating spindle sander for woodworkers. I want to build one not just because my friend Nick sent me this cool kit and I want to build it, but also because I think it's going to be a very useful thing for my locomotive project. And hey, die filers, a bit like shapers and D-bit grinders, are having a bit of a moment among the cool kids on machinist YouTube. And who's got two thumbs and won't turn down a seat on the bandwagon? This girl. Oh, yeah, I was pointing at myself with my thumbs there. Yeah, YouTube isn't really a visual medium, so that joke didn't work as well because you couldn't see what I was doing. Anyway, let's move on. What I really like about this kit, though, is that it comes with really extensive build notes, which is much more than you usually get in machining kits. Normally you get some drawings, some castings if you're lucky, and you're left on your own to figure out everything else. So this is quite detailed. There's suggestions in here for setups, and even some notes from other people who've built this kit and have given suggestions back to Andy that he's incorporated in here, so really quite complete. As one does, I'll start by fettling the castings. They're actually pre-fettled, which is very unusual. Someone has already taken an angle grinder to much of the casting lines here. I just cleaned up a few more of them here with the Dremel. Normally there's a lot of work to do here on castings, but these are actually almost all the way there. Then something I've been doing lately on cast iron when there's a big cut to do is taking an angle grinder to it first, just to remove that outer boundary scale. That scale often has sand in it, which is hard on tools, and it's often very hard. Sometimes there's even little bits of glass in there, so I find it cuts much easier if you grind that off first. The traditional wisdom on that is to just take an initial cut that's deeper than that scale, but that just isn't possible on small machine tools, so you end up chiseling your way through it and resharpening your tools 6 times. All right, let's get sketchy. This kit has been designed to be a lathe-only project if you are so inclined, and while I'm sure you can do it with a lathe-only, some of the operations, such as this one, are a little bit terrifying. The build notes suggest holding on to that top boss there in order to face the bottom of this casting to get the first reference surface. So I set that up to see what it would look like. Here it is spinning up just so you can get a sense of what this would be like. It would need straightening, of course, but I'm actually not going to cut it this way, and I'll show you why. Because of the draft angle of the casting on this boss, you can see that only one tooth is engaged on this jaw here on the chuck. Same on the opposite side of the chuck. The other 2 jaws of the chuck are okay because there's no draft angle on the casting on this axis. So I'm not very comfortable with the grip here that I have. If you wanted to do it this way, I think you would need to turn that boss down a little bit and make the sides of it parallel so you can get a good solid grip on it. If your chuck was big enough to hold that casting by the base, so you could flip it around and turn the boss and then flip it back to hold the boss, I think that would be fine. Another way to do that would be to turn that boss down using a boring head with an outside cut on the milling machine. And I considered doing that, but then I thought, if I'm going to go to the trouble of setting it up on the mill anyway, I might as well just use the mill to face the bottom. So that's what I'm going to do. What's interesting about the bottom surface here is that there's draft angle in both directions on it. And because of the size of the surface, the slight angle of the draft ends up being quite a large distance end to end that the surface drops off. So what I'm doing here is I'm trying to balance that drop off I want to get this surface as parallel to the table as I can, so I'm going back and forth with the indicator and trying to get the outside edges to be at the same height. On the x-axis, I'm doing this by lowering one side by sliding those V-blocks away from the casting, and that lowers that side. The reason that works is because, as you can see here, there's draft angle on these bosses in this direction. So when I move that V-block away from the casting, that boss drops down a little bit because of the angle of the casting. So I went back and forth on that until I had the same amount of drop off from center on both sides, which ended up being about 150 thousandths, quite a bit. And then on the y-axis, it was a simple matter of using that machinist jack there to lower the nose until once again I had the same amount of drop off front to back, which again was about 150 thousandths. I also want to get the nose on that casting parallel with the y-axis of the lathe. So to do that, I've got an indicator on the side of the casting here. There's no draft angle here, so I should be able to indicate this in more or less. It's still a rough casting, but I was able to tappy tap tap this pretty straight here. The reason for this is that I'm going to be drilling the bolt pattern in the base in this same setup, so I want that bolt pattern to be aligned with the nose there on the casting. My weapon of choice for this cut is the Shrum Solutions Tri-Fly. This is a 3-insert face mill, and it's basically a face mill for small machine tools, which is really great because the big girl facing mills have too many inserts in them, and the tool pressure is too high for a little mill like this. So this is a little baby face mill, and it's perfect for little baby mills. I used to use shell mills for this type of thing, which I think are still a viable option for small machine tools. You'll see me using those in a lot of my earlier videos before I had this tool. The problem with shell mills is that they're a complex geometry cutter, and when you dull them, or like I did, you drop it and chip one tooth, they're very difficult to get reground, and they're kind of expensive. So this is a really good alternative. It's just inserts, so you can replace the inserts, but the tool pressure is still low enough for little machines. I mean, you could also rough this in with a 1/2-inch end mill. It would just take a lot longer, and then maybe finish it up with a fly cutter. There was a lot of material to remove here. It took about 200 thousandths to clean this up because of all the draft angle, like I said, but it went pretty quickly with this tool. I was doing 25 thou passes at 700 RPM, and then I finished up with a 5 thou pass at 850 RPM, and that left this really beautiful finish that you see here. It even passes the scale reflection test. There's 2 little corners here on the front and back that didn't quite clean up. Those might have been me with the angle grinder, or they might have been my predecessor who pre-fettled this, but I'm not going to try to clean those up. I'd have to remove way too much material to get to the bottom of those, so I'm going to leave it here. And one thing about machining cast iron, you will find all the magnets in your shop. Next, I want to find the center, and for that I was going to bust out my spindle mounting indicator here. This is a shop-made tool that I have a video on, and as you may recall from this older clip here, it does not fit on the spindle of my new mill. So I thought, okay, now's the time to fix that. I took it apart and I set up that ring here carefully in my forejaw using a button indicator with a lever arm on it there to dial in the center. And I've got a piece of shim stock clamped in it there so that I can make it round and open it up while maintaining the clamping gap there. With that dialed in, I used a boring bar that can reach around the stem there that's Loctited in place and open that up to the size of the new mill spindle. So that all seemed to go very well and nailed the dimension that I was looking for, so now I can put this back on the new mill, and yeah, I blew that dimension somehow by 20 thousandths. Every so often, I make a really big mistake like that, and I honestly don't have any idea how it happened. I think I must have misread the micrometer when I was measuring the new spindle. I'm not sure, but I blew that dimension by a country mile. It happens sometimes, so I'm going to have to remake that ring, but I'm not doing that today, so I just put some shim stock in there, and yeah, this will get it done. Normally with this style of indicator, you just sweep it around the surface to indicate it in, but I didn't like the way the needle was dragging sideways on that rough casting surface, so instead I switched to just sampling the surface vertically here at the 4 relevant positions. And this was working fine, and I proceeded to dial this thing in, but after a while, I just wasn't winning. I was going around and around and around and making adjustment after adjustment after adjustment, and I just could not get it dialed in. Usually I don't have difficulty doing this, and I just could not get this thing to cooperate. So then I started taking measurements of this disc, and it turns out that this casting base here is about 50 thousandths out of round. And that's more than the range on this DTI. So I wasn't able to indicate it in because it's so out of round that the DTI can't even detect it. That required a change of strategy. Now this center doesn't have to be super accurate, it's just to get my bolt pattern roughly in the correct place. So I decided to switch to an old school method. I grabbed the center finder and scribed a series of lines. I normally only do 3 of these lines, that's sufficient to get the center, but this thing was so out of round and I didn't know where the out of roundness was exactly, so I did a whole bunch of lines until they sort of converged on a blobby polygon in the middle. Then using my little wiggler style pointer here, I was able to use some magnification and kind of estimate where the center of that blob of lines was. And it was good enough for the bolt pattern on the base here. Then I started by center drilling this and then drilling through the clearance hole size, which is specified in the drawing as 5/16. Now the reason I'm doing this is not just because I have the setup here already, it's because I'm going to be using these holes to mount this casting to my faceplate. I do have some operations here where we need to set it up in the lathe, but as I said, I'm not very comfortable holding it by those bosses and such, but I am comfortable bolting it to my faceplate. Not shown in the midst of all that was the good 40 minutes I spent cleaning up my shop after machining all of that cast iron. That was a lot of material to remove, and that entire corner of my shop was a disaster when I was done. I'm glad it's over though, and now I can get this thing set up on my faceplate for the next couple of operations. And in a first in the entire history of machining, the holes already lined up with 2 threaded holes that I'd put on this faceplate previously for some other operation. This is history, folks. You saw it here first. Next, the way cover comes off because it does not clear my faceplate. That's why I put quick release thumb screws on it. I have a video on making that way cover if you're interested. Then on goes the faceplate. Moment of truth. Let's see how true this thing is running here. And the answer is not at all. It's out of concentric by, 200 thousandths or so. Yeah, that's fine, right? No, it's not fine. Just for comedy value, let's spin that up and see what it looks like. Hilarious. Alright, so we're going to have to do better here. I'll see if I can tap it in. It's mounted with 1/4-20 hardware, and the clearance holes are 5/16 in the base, so I may have enough wiggle room here to tap it in. So I tapped it in as best I could, but the answer is no. I did not have enough clearance in those holes to get it running even close to true. We're still out by about 100 thousandths. Plan B, I took it back to the bench and I'm going to transfer punch some new mounting holes here. And these are going to be large clearance holes, so I'll have a lot more room to tap it in. Took me a couple of tries to get some punch marks that were not too close to other mounting holes already on the faceplate, but I found some that should work. Then I took it over to the drill press and center drilled and drilled those out. These are 3/8 clearance holes. So with the 1/4-20 hardware and the 5/16 holes in the base, there should be plenty of tapping room to get this thing running true. After deburring, I also went over it with my precision ground flat stones. I have a bunch of extraneous punch marks there, and there might be some burrs on the holes that I drilled and so on, so just going to make sure everything's nice and flat. These precision ground flat stones really are magic. These are from 26 Acre Maker, Lance Ballsy, but you can get them from other sources as well. And here's a close-up so you can kind of see what they do. There's one of those punch marks that I didn't want, and you can see how there's a shiny spot around it, and that's where the little volcano of material that a punch mark creates has been removed. So all the high spots are gone, but none of the faceplate around that punch where it was already flat has been touched. So it doesn't scratch anything or it doesn't create any other low spots, it just takes the high spots off. Precision ground flat stones really are amazing things. They're a lot of fun to use. Back on with the casting now. I'll get it roughly tapped in, centered here, just using a scale. This should get me within 50 or 100 thousandths, which will make my job a lot easier over on the lathe. And back over to the lathe we go to get this thing tapped in for real. Tapping in parts on the faceplate is a bit of an art. The secret is to start with the part tight, and if it won't move, then loosen the mounting bolts, but just a very little bit, like maybe 10 degrees. There's a magic sweet spot where the mounting hardware is tight enough that it will hold the part vertically on the faceplate. It won't slide down under its own weight, but you can still get it to move with the hammer. And that will allow you to dial it in just as if it was being held in a 4-jaw. Sometimes you'll be tapping and it'll get stuck, especially with a casting, because casting surfaces are rough and again there may be draft angle. So in that case, loosen the bolts a little bit more and it should start moving again. If it gets completely stuck, then odds are you've run out of travel on your mounting hardware and you have to go back and either enlarge clearance holes or mount the part a different way and so on. However, after a good 20 minutes of tapping and spinning and tapping and spinning, I just could not get it any better than about this. I've got it within 10 thousandths all the way around, except for one like 50 thou high spot. So again, I took some measurements and found out that this boss, again, is a good 30 thousandths out of round. So getting it dialed in was really not very possible. So that was really the best that I could do. And in fact, if I spin it up, you can see that not only is the boss out of round, it's actually a little bit crooked relative to the casting features under it. So I suspect that the patterns being used for these castings are perhaps worn or something along those lines. But we got it dialed in good enough for what we need here, so this will work. After all that though, I was not happy with where things were at. You can see what's happened here is I've used threaded rod because I didn't have any bolts long enough. And when I tightened those nuts down, because of the angle of the casting on the back of the faceplate, the threaded rod has bent. And maybe that would have been fine, but you know, that's now fatigued and I didn't trust it anymore. So I wasn't very comfortable spinning it up with 2 bent threaded rods holding it in place like that. So I ran down to the hardware store and I got some grade 8 bolts the same size to replace that threaded rod, and I set it up and dialed it in again. This really didn't take long though, because by now I was very used to the quirks of this casting and I knew how to dial it in around its big lumpy spot and the weird crookedness of it and so on. With it running reasonably well, the next thing I wanted to do is add some counterweight. Because of the nose there that's sticking out on one side, this casting is going to be pretty out of balance weight-wise. So I added some lead strips opposite that nose here. You can buy lead in rolls and it cuts very easily, and it's great for making counterweights for setups like this. So I bolted a couple of strips of that on there, and let's spin it up and see how that behaves. You can tell how well balanced it is by how fast you can run the lathe before it starts shaking itself into the next county. In my case, I got it up to about 150 RPM before it decided that it no longer wanted to be on the bench, but I needed better than that, so I added a couple more strips and spun it up again, and I got it up to about 300 or maybe 350 here, and that's enough RPM for what we need to do here. Next chips then are going to be to face this boss as is tradition. The goal here is to create a flat spot for a big boring operation that we're going to be doing. And it turns out we need to face this boss down quite a bit to get to the required dimension. The references on the drawing are all from the bottom of the base, so I'm checking that here. And around here is where I realized what I really should have done is done layout on this casting. Casting layout is a bit of an old school technique that you see in the old books, such as this one. What it allows you to do is figure out where all the features are going to land on the casting before you start making chips. So you know if your first cut is deep enough or too deep, and you know how much to remove off all of the other sides of the casting. But I was already committed to this setup, so I was just taking measurements as I went here. After a few more cuts, I started to get close to where I should be. I was taking some final measurements here, but the numbers just weren't adding up. The overall height of the final casting is given in the drawings, but when I looked at how much I was going to need to remove to get there, I had nowhere close to that amount available on this boss. So I thought, well, maybe I was supposed to remove more from the base, but there wasn't even close to enough material there either. I was going to be left with a paper-thin base. So I was doing the math and trying to figure out, is there enough material to remove from both top and bottom to land at this dimension? And it just wasn't even close. For whatever reason, this casting was a good 3/8 to half an inch too tall. There was just no way to reach this overall dimension here. So after thinking about it for a while though, I realized that what really matters is the relationship between the top surface and this boss and this center line here, because that sets the relationship between the drive eccentric inside the mechanism and the table height and the position of the file. Those are the relationships that matter. So really, the reference should be this top surface here. With that in mind, I flipped all the dimensions to be referenced from the top surface instead, and suddenly everything started making sense. I was very close to the correct dimension to these side bosses where the table mounts, and I was also very close to where the drive shaft down the center of the nose there needs to be. I just had a little bit more material to remove, and I was going to be right on both of those dimensions. So I don't know what happened with the base, why it's so off, but relative to the top surface, everything makes sense. So that's what I did. Now, lest you think this casting is some sort of disaster, it really isn't. The build notes are very clear that none of these dimensions are especially critical. You can easily adjust and adapt all of the mechanism as you go along, and it's very, very forgiving of all of these dimensions. I should say here that while I've had some challenges with the geometry on this casting, the metallurgy of it is excellent. There's no chill spots, no inclusions, it's machining really beautifully, which is not always the case with cast iron kits. I'm getting ready to do the big bore now, but I was still feeling uncomfortable about how much trouble I had dialing in this boss, so I wanted to sanity check if I was sufficiently on center here. This is just cosmetic at the end of the day, but I want this thing to look good. So I got out the center finder again, and I drew some scribe lines here to just kind of use another method to check for center here. And sure enough, when I got the center drill on there, I was pretty much perfectly on there, right in the middle of the little triangle formed by the center finder. So that's really as good as this boss is going to get, even though it looks like there's quite a bit of run out when it spins up. This is going to be a very challenging boring operation because it's a hole that isn't very big, but it's very, very deep. And that's the trickiest type of boring that you can do. I'm going to start by pilot drilling here with a small drill. There's two bores, one at each end of this casting, that have to be as perfectly aligned as we can get them. The actual diameter doesn't matter a whole lot, it's really the alignment that we're worried about. So with the first one pilot drilled, I then came in with a long aircraft drill the same size and hoped that the outer pilot hole would hold this drill still enough that it would get a reasonably concentric start on the other side there. And it did wander a little bit, so this hole is a little bit off center because of the roughness of the casting there. The drill had trouble grabbing and starting to cut straight, but that's okay because we're going to be boring this out in the end, so this is all just pilot drilling that we're doing. We're going to get our concentricity back with the boring bar. Now, anytime you're drilling, whatever's going to go wrong is going to go wrong right as the drill breaks through to the far side. If it's going to break, that's when it'll happen, or in this case, if you're going to spin the drill in the chuck, this is when it's going to happen. That is a bummer. I really hate doing that to my drills, but you can see how little of the drill I was able to hold on to there and still have enough length to get through. That was unfortunate, but there was nothing to it but to put the chuck back on, and this time give it a lot more Wheaties, and that was enough to finish the job. Now I follow up that pilot with a 1/2-inch drill all the way through both of these two bosses. And this was cutting very well. This is cast iron, so I can go straight from that small pilot up to this larger drill, even on my small lathe, no problem. Cast iron cuts very, very easily. And even though this is just a regular jobber length drill, again, I had just enough length to get this done. I was, again, holding on to the very end of that drill towards the end. I kept having to pull the drill out a little more and give myself a little more reach so that I could just break through while still hanging onto the drill. You can see how close that is there. I don't know, call it Quinn's first law of drills. They're always slightly the wrong length. A little too long or a little too short. I need a little more diameter yet though for my boring bar, and contrary to popular belief, I do actually own a handful of Silver and Deming drills, or reduced shank drills. Found this one in the junk drawer. It's a random size with an unknown grind on it, but it seems to be cutting just fine. It's 25/64 for some reason. I don't know why I own this, but I do. I think it was sent to me by a viewer at some point. But it's cutting very well, and once again, it was just barely long enough to do this. And metric fist pump of victory, thanks to that random Silver and Deming drill I found in the junk drawer. Now I've got enough room for my largest boring bar. This is a Shrum Solutions 16mm solid carbide boring bar. Solid carbide is key here because I'm going to make it do some very antisocial things. But to start with, it's got an easy job. I just need to bore through the upper boss here, and hey, clearance is clearance, friends. That is tight, but it does fit. My target dimension here is 875, which is going to be very important here in a minute. In principle, that dimension doesn't matter because we're going to be pressing bushings into here, and you can turn the bushings to fit. But I do want to hit exactly 875, so I'm taking my time here. Luckily, that Silver and Deming drill got me very close to the final bore size, so I didn't have a lot of work to do here. I got a really excellent finish in there. That boring bar did a beautiful job. Now I'm going to extend this boring bar as far as I possibly can to see if it's going to be long enough to finish the lower bore. And I went so far as to push it so it's only held by 3 of the set screws in the tool holder. And I got that as close to the casting as I possibly could. and still it just wasn't enough. I took some measurements here of how far I had to go and how far I could reach, and I was coming up about an inch short. At this point, I had a few options. The first option I tried was to source a longer boring bar. And again, there's only room for a 3/4 inch bar here, and there is no commercial bar available that could get the depth that I needed here. So I was even prepared to eat the overnight shipping cost here to keep this project on track, but there's no boring bar that will do it that you can buy. So the next option would be to make a 3/4 inch boring bar that's long enough to do it. This being cast iron, and with light cuts, you could probably get away with a bar that long. However, the lathe is tied up, so I can't make a boring bar easily here. I can't take down this setup because remember, the alignment of the two bores is crucial, and I've finished the outer bore. So I can't touch this setup until I have a solution. I considered going down to my local welding shop and just seeing if they have a piece of 3/4 inch round bar, and then I could just drill a hole on the mill and put a piece of high-speed steel in it, instant boring bar. That probably would have worked. Another option suggested by a patron would be a large reamer, and that would work as long as it was a jobber length reamer, which in the case of reamers means that the cutting flutes, not the overall reamer, are extra long. That's necessary because in order to maintain alignment between the bores, you'd want the flutes engaged with both bores at the same time. Reamers dimension precisely, but they don't hold alignment unless they're put through a pilot hole, which is already well aligned, which, as you may recall, mine is not because those pilot drills wandered a little bit. Really, boring is the best option here to guarantee concentricity. The plan I decided on was determined by digging through my junk drawers again and finding a 7/8 silver and Deming drill. Again, I don't have many of them, I don't have a full set, but I have a few random ones, and 7/8 happened to be one. It had a very dodgy grind on it, but for my plan, that won't matter. So I took that boring bar again that I have, extended to a ridiculous degree, and went in and bored the far side as far as I could with this boring bar. Again, this is extended way past what's ever recommended for any boring bar, and certainly more than this one should be, but because this is cast iron and it's running relatively slowly, just 300 RPM, and I'm taking light cuts, I didn't get any chatter, and I got away with this. I was able to bore the top half of the lower bore to the correct dimension. Now, measuring it was a little tricky, but I was able to sneak in there with the telescoping bore gauge and take some measurements. Later I figured out these shenanigans weren't necessary because, of course, the inner bore is smaller than the outer one, so I can pull the gauge all the way out through the outer hole without disrupting the measurement. Now that I have 1.5 perfect 875 bores, I can take that silver and Deming drill, which I polished to be a nice sliding fit in the bores there, and I can slide it in, and I'll be able to finish the lower bore with the drill. I oiled it up real good because it's effectively running in bearings at this point. The outer bore and the partial inner bore are fully supporting this drill. And what that's going to do is make this drill cut extremely accurately because it's fully supported at both ends of the cut. It really can't wander off and cut oversized like drills often do because it's so well supported. You could say I'm sort of line boring with this drill if you like, because it's perfectly supported at both ends. I wasn't sure if this was going to work, but I felt pretty good about it. And I didn't have far to go to finish that lower bore there. Once again, this drill was just barely long enough to do it, but it did do it. And again, the key to success here is that I was able to do half of that second bore with the boring bar, which thus reacquired concentricity on that bore so that the drill wasn't left to follow the wonky pilot drilling that had occurred. All right, moment of truth. Let's see if my little stunt with that drill with the dodgy grind on it worked. I'll get things deburred here. I certainly have a bore. The finish in it is not quite as good as the other end where it was done with the boring bar, of course. Drills don't leave as nice a finish as single point cutting does, but dimensionally, survey says, and would you look at that, that is within 2/10 of being dead nuts. So it just goes to show drills can cut accurately as long as they have a little bit of help. So I got away with that and I'm very pleased with the result. It doesn't look like much yet on this casting, but you saw all the effort it took just to do these few operations. This is a big casting with some tricky setup on it. There's lots more to do on this casting, but that is all the time I have for you this week. Thank you so much for watching. I hope you enjoyed it. Thank you to my patrons who make all of this content possible, and I will see you next time.